Welcome, everyone. This morning, we're going to talk about what happens when we take a completely different discipline, known as the complexity sciences, and fuse that together with software engineering to change the way we think and talk about architecture as a problem, which is going to change the kind of solutions that we use to deliver software architectures. And what we'll talk about this morning is kind of the culmination of a 10-year research project that I've been involved in. So the problem that we're trying to solve is, why is software architecture so difficult? Why is it so hard for us to express how we arrive at a design? Why is it so hard for us to agree about how you should arrive at a design and what that design should be? And why is it so difficult to teach junior software engineers to become architects? And the only real way we have of teaching them is just to allow them to bleed for 10 years until they get used to the suffering. There's a number of major problems within software architecture that we don't really talk about enough. And the major thing that affects us is these three things here: time, change, and uncertainty. When you look at how we express architectures, if you look at tools like UML or Archimate or anything that we use to document our architectures, they tend to be very static, two-dimensional things that give you a snapshot of your architecture. There's no way in these tools to represent time. And why is it important to represent time? It's because we all know that an architecture, on the day that you draw it, will not look the same in 6 weeks or 6 months or 6 years. It changes constantly. And so the reason time is important is because things change over time. And why do we duck this problem? Why don't we deal with it? It's because we don't know what's going to change. So it's easier to just sweep it all under the rug and draw a two-dimensional diagram and hope that nobody points out that we don't know what's going to happen in the future. These are the three things that make software architecture both difficult and extremely necessary. If things didn't change over time in an uncertain way, then we wouldn't need architecture. We could just write code and deploy it, and we'd be done. We wouldn't have to think about it again. Another problem we have is that we don't really have a consensus yet around what it is that we do. And you can see this if you ask the very simple question: what is the unit of software architecture? What is an architecture made of? How is it built up? And if you go back in time, all the way back to ancient Greece, people realized that we need to have some kind of idea of what everything else is made of so that we can gather around a number of concepts and begin to do some real work and discuss things. There needs to be some kind of agreement about what everything is made of. And their original ideas, looking back on them now, seem a bit silly when they said things like everything is made of either earth, fire, wind, or water, if we go back to Aristotle. And that looks a bit silly now, but it was actually a very useful conversation because it took us on that journey of we need to be in agreement about what the base unit is. And in modern physics, the atom is the base unit that everyone can assemble around and agree and say, yes, everything is made of atoms. This gives us a model of the universe, and everything is built from there. Or the Newtonian particle, if you're doing mechanics. In chemistry, they have the molecule. Everyone can assemble around this idea of a molecule and say, yes, we all agree, there are molecules, everything is made of molecules, that's how we should talk about things. In biology, they have the cell. And this is the start of a serious science. We can start to do some real work. It's an important conversation to have. In software, we've been on a bit of a journey. And I don't think we're quite finished yet. And we've been moving through all these different ideas of what the unit of software might actually be. From the machine to the punch card to the object, there's a bit of a strange turn, to the service. Today people can get very passionate about functions and microservices, and you'll even see things like processes and features and patterns turn up. How should we describe our software architectures? And very often you get a bunch of architects in a room and a bunch of developers. Everyone's looking at things from the perspective of a different unit. It gets very confusing. So in today's talk, I'm going to introduce an entirely new kind of unit, which is called the residue, and the purpose of this unit is to capture time, change, and uncertainty in our architectures. So what we're going to go through this morning is kind of heavy, It's a big, big subject. You won't entirely grasp everything after 45 minutes. Don't stress. You can always come back and watch the video later. So there's a couple of concepts we have to get to grips with before we jump into this. So when we work, we generally work with systems, and a system is just a bunch of stuff connected to other stuff. And there's different kinds of systems. So there are ordered systems, and ordered systems are systems where the components of the system are highly constrained. They don't have a lot of wiggle room, and because of this, they can be predicted. Their future states can be predicted. And when you test an ordered system, you get roughly the same behavior every time you test it. And they're quite nice and comfortable and easy to work with. And this is the focus of engineering. And software, by that definition, is an ordered system. And a car is an ordered system. A car might have 30,000 parts. It might be really, really complicated and hard to understand, but it still behaves in this way. It's ordered. On the other side of that, we have disordered systems. And disordered systems, the parts of the system are loosely constrained. They have a great number of degrees of freedom within the system, and this makes the disordered system unpredictable. And if you look at a disordered system, your engineer's mind might see some patterns, but you'll find that those patterns won't stay still. They keep moving, they keep changing. It's very difficult to work with these things from an engineering perspective. And human systems and business systems are disordered systems. You can't. And the problem is, with these two kinds of systems, you need a completely different mindset, a completely different set of tools for dealing with them. Now, if you're a software architect, most of your training, most of your university training, most of your early career is focused on this little box here, this ordered software system. And our job is to define a structure for this software system and say, it's this many components connected in this way, and they're going to behave in this way. And it's an ordered system. It's predictable. It's testable. It is not in any way complex. And this is what we're trained to do. And engineering tools will help us to do that. The problem starts when we take this poor, innocent, naive little architecture and we put it into this mad, pulsating mess that we call a business, that has people in it, and it has a connection to the economy, to competitors, to a market, to a society. And it's moving all the time, and it's completely and utterly disordered. And what happens in this disordered system is that sooner or later, you're going to get this X that pops up, this unexpected event that nobody knew was there, that nobody could have predicted. And the problem with this X, of course, is that there's always more than one of them. There's lots of them. And when they pop up, they immediately put pressure on our software structure, and they start to push on it. And it cracks, and it breaks, and it splinters. And it makes it look like all the architectural decisions we made were kind of silly in hindsight. And someone will come along and say, why did you do it like that? You should have done it like this. It wouldn't have broken. The way that we traditionally solve this in software architecture is with this magic thing called scope. And we just draw a ring around it, and we go to our business stakeholders and we say, everything that you tell us about the system is in scope, and everything that you don't tell us is going to happen in the future is out of scope. So this is a you problem, we say to the businesses. And then we work happily inside this little scope circle, and we can never be wrong if we're building to a specification that we demand that these business stakeholders tell us. The problem with this approach is that it doesn't make reality go away, and eventually an X will pop up, something that our stakeholders can't, because they can't see the future in this disordered system either, and it will break our architecture. And if you're using scoping and contracting to do your architecture, then in this way you can get paid a second time and a third time for doing the architecture. So it's a fantastic business model that we maybe are a little bit reluctant to step away from. Now, if this was the way it always was, there's only one way to solve this problem. And the only way to solve this problem is to be agile and say, we can't see the future, we can't do anything, let's just deal with X when it pops up. The problem with that is that all across the world, there are tens of thousands of good architects who consistently deliver architectures that survive this problem. And the architecture survives for a very, very long time, despite the fact that that architect did not know what the future held. And the question then becomes, if they can do it, why can't you do it? That's a good question. And so we look at those architects and say, what is it that you do that makes these systems magically survive when you don't have the spec, whenever the reality that's going to be uncovered isn't available to you? How do you solve that problem? And in order to get a grasp on that, what we're going to do is step back and we're going to look at software engineering from the perspective of the complexity sciences. Because it's a very, very different perspective than the one that we take. The way that we've been trained and taught to look at software engineering is from the perspective of classical and traditional engineering with its blueprints and its specifications and its testing and its rigor. And that doesn't work in a disordered system. And so software, from a complexity perspective, turns out to be really, really interesting. So I'm going to introduce two tools from the complexity sciences to help us understand what it is that we do and what it is that these senior architects might be doing that makes them able to do what seems to be theoretically impossible. The first thing I'm going to talk about is random simulation. And it works like this. If I give you a problem to solve, a square of side x, and inside that square we have a circle, and I ask you, what is the area of the circle? I'll give you half a second to think, and I want you to be honest, if you haven't seen this talk before. The engineering impulse is to measure and be precise. And the first thing, if you haven't seen these ideas before, that you're going to do as an engineer is look for R. Because you know I can plug that into pi r squared and I can precisely answer this question. That's how it works in high school math. That's not how the real world works. The real world is messy and nasty. The way that we solve this kind of problem in the real world, because you can't actually get to R. You can't measure it in this diagram, not least because it's badly drawn. What we do is we just throw a dart at it. So we throw a dart at the shape, and the first dart I throw hits the circle. And the second dart I throw misses the circle but hits the square. And based on those two random data points, I'm going to make the conclusion that the circle must be half the area of the whole shape, right? Because half the darts hit it. And therefore, the area of the circle is x squared over 2. Now, I take a step back. How many of you have felt deeply uncomfortable when I said that? Right? That it doesn't feel right. There's something intuitively wrong. For us, we've been taught to work with ordered systems, and I'm teaching you now a method that we use to deal with disordered systems, and it feels wrong. It's not precise. It turns out that actually this is a bit ridiculous. 2 darts is wrong, but if you throw lots of darts, you get closer and closer and closer to the actual answer. And it's called a random sampling, or random simulation is when you're creating the data points yourself. And not only will this work for circles, it will work for any shape that you can think of inside the square. When you do requirements engineering, and you talk to stakeholders, and you listen to their language and you analyze their language, when you do risk management, and you make up numbers and call them probabilities to give yourself some credibility for what you're doing, are you measuring precisely and telling us what R is, or are you just throwing darts? I leave that up to you to think about. A second thing from the complexity sciences that's important is the concept of a Kaufman network. Kaufman was a complexity scientist who worked in the 1960s, a biologist, the question he was trying to answer is, how does life come to be? How do we get from a bunch of amino acids floating around in an ocean to, in 1966, when he was doing this work, how do we get from that to the Beatles? How does that happen? And he came up with a model to describe the behavior of these basic sort of biological systems, and he called it an RBN, a random Boolean network, which later became known as the Kaufman network. And the network, and these little circles here are nodes in a network, which is where the N comes from. Boolean means that every node in this network has only two possible values. It has a value of 1 or 0. And a good way to think about this is to think of this network as a set of light bulbs. And so it's not 1 or 0, it's on or off. And it's random because every light bulb has a tiny little piece of code unique to that node that when it gets an electrical signal, it randomly decides, am I a 1 or a 0? And so you put a little button down here, you press that button, and all the light bulbs get an electrical signal, and they all run their little function, and they decide, am I a 1 or am I a 0? So every time you press the button, you get a different pattern of light. What that means is that for this network, the number of possible states that this network can arrive in is 2 to the power of n, where n is the number of nodes in the network. And Kaufman ran this with n set to be 100,000. Okay. On a computer simulation, he didn't have like 100,000 light bulbs. It would have been expensive in 1966. And 2 to the power of 100,000 is an enormous number that does not fit in our heads. We can't even contemplate how big that number is. If your requirement specification has 2 to the power of 100,000 elements in it, you're already done. It's over. Give up. Our human systems are actually way more complex than that. Then he did something really interesting. He linked the nodes together. He connected them, and he allowed a node to send a signal after it executed to a neighboring node to say, I'm a 1 or I'm a 0. And then he allowed the neighboring node, when it received that signal, to recalculate its own on or offness. And so when you press the button now, you'll see a little bit of blinking in the network as they all make decisions and communicate with each other. And when he did this, he noticed something strange. He noticed that despite the fact that you would, in the first instance, without the links, you would have to press that button until the heat death of the universe before you would see the same pattern of light turn up again. He noticed that he was seeing the same patterns turning up over and over and over again. And he counted them. And there were 317 patterns that turned up over and over and over again. 317, you've probably already calculated, is the square root of 100,000. So he went from 2 to the power of n to root n states. Now 2 to the power of 100,000, if that's your requirement spec, it's over. 317 is still nasty, but it's doable. It's at least approachable. And he called these 317 different states, he called them attractors, after the Lorentz attractor. And the reason they're called attractors is because it feels like this system is attracted to that state. It keeps returning to it. And the thing that makes it return is the connection to other nodes. And when they start to influence each other, the number of states in a system gets much, much smaller. These attractors are the reason that we can exist in this universe at all. It's the reason that we can negotiate the world around us, is because things are roughly similar a lot of the time, and that's because these very complex systems that we live in all pull towards the same thing. It's the reason that bees and bats and birds all develop wings, despite the fact that they didn't get together and have a committee about how to do that. He noticed a number of things about these networks that were interesting. 3 numbers that are important. The first number is n, the number of nodes in a network. The higher n is, the greater the number of attractors, the more work you have to do to deal with that system and understand how it works. It makes sense if the attractors are root n. The other value is k. K is a measure of the linkage of the system. How connected are these nodes to each other? And he noticed that as k rises, the system gets more and more attractors, and it becomes more and more unstable in the journey between those attractors. And the third value, which is a little bit more abstract, is called bias. And bias works like this. If I have a node here, and it sends a message this way half the time, and this way half the time, then it has no bias. It's democratic in the way it sends its messages. But if I take this node, and I force it to send a message this way 2 times out of 100, and this way, 98 times out of 100, then we can say that that node has a high degree of bias towards a certain course of action. It will, most of the time, communicate with that lower node. And what we've done is introduce bias to that system. And what he found is that you can raise n and raise k, and the attractors in the system will rise, and it will become more unstable and harder to manage. But if at the same time you raise p, then the number of attractors falls, and the system becomes easier to manage. And this might be a little bit abstract, and it might feel like, ooh, this is a lot of detail, I don't really understand this. As a software engineer, you've been doing this for your entire career. When we make decisions about the size and shape and the number of components in a system, we know that if we raise the number of components in a system, you're going to get more attractors. It's harder to manage, harder to deploy, harder to troubleshoot. So anyone who's done any microservices should have learned this lesson by now. Should have. If you raise the number of attractors, if anyone's done any enterprise integration, you'll know if you let systems connect to each other, if you let microservices connect to each other willy-nilly and the number of connections rises, that the system becomes unstable and presents a number of attractors that makes it hard to manage, hard to troubleshoot, hard to change eventually. And when it comes to P, we bias our components all the time. And the best example of bias in our industry are the tenets of service orientation. When we say that all of our components are going to communicate through a schema, through a contract, they're going to communicate with a certain policy, with a certain security protocol, they're going to present error messages in a uniform way. All of that we are doing is introducing bias to our components. So we've been doing these things all our careers, but no one's ever thought about linking this to what Kaufman did in the 1960s. And what this means is that software engineering, from a complexity science perspective, is really just a two-step algorithm. It's a random simulation of the environment followed by an NKP analysis of potential software structures. The NKP is these three numbers here, N, K, and P. Yeah. So the problem is that when we execute this two-step algorithm, firstly, our random simulation isn't random enough because we introduce bias to it. We talk about what we believe is going to happen, not the entire phase space of what's in front of us, and we filter by probabilities which we make up. And so we ruin the random simulation by introducing our bias to it. And the NKP analysis is implicit. We do it, but we don't have a common way of talking about it. Everyone has their own favorite method or favorite way of talking about how we arrange our components, and we have no uniform way of understanding that. The NKP analysis, it doesn't matter whether you believe in domain-driven design or some other way of breaking your components down, or your system down into components, the NKP analysis is always there in the background implicitly. Residuality theory then, which is this theory that I've invented as part of my PhD project, does two things. It makes the simulation more random. It gets rid of that bias and that filtering, and it makes the NKP analysis very, very explicit so that we can be honest about what it is that we're doing. And residuality theory is basically a theory of applied complexity, and it works like this at its base level. What we are working with is a system, and a system is just a bunch of things connected to other things. And the first thing that residuality theory says is that you cannot map this system. And this upsets the enterprise architects. You cannot sit down and draw it. You cannot write it. You cannot capture every detail in this system. There is too many moving parts. There's too much happening. And even if you did manage to write it all down, it would have changed by the time you'd went to the printer to pick up the 10 million pages that it printed. The Agile movement figured this out a very long time ago. And so what we want to do is we want to be more scientific about architecture. And so what we're going to do is we're not going to speculate. We're not going to say anything that we cannot prove is true. We're not going to make things up because that gets us into trouble. And so the only thing that we can say about this thing that's actually true is that something is going to happen because it's a complex system. If nothing happens, and we're wrong about that, then it's not a complex system, and you can probably write it all down. It also means the system's dead. This is X, though. We don't know what's going to happen. We don't know when it's going to happen. We just know that something is going to happen. And when that something happens, the system is going to be changed after the happening. It's going to be a slightly different system. And we call this leftover system, we call this the residue. It's what's left over after something changes. The residue is also a complex system, so the only thing we can say about that is that something's going to happen, x dash. We don't know what that is either. And this doesn't seem very useful at this point, but it gets better, I promise. What we can say about the next step is that the system that's going to emerge in this third step is going to be a function of the system that was in the last step. So the residue is going to influence the future. It's going to be there in some way. As architects, the only thing that we control is the residue of the software part of the system. We get to control what's left over when X hits the system. Everything else is beyond our ability to grasp or predict or control. There is no scientific recourse to being able to do any of that. And this is a very skeptical way of looking at the world. And it's necessary to get rid of all the bluster and all the noise and all the promises that we've been making for a very long time. What does this mean for actual software engineering then? The first problem that we've just solved is this. When we take our innocent little software system and put it inside this complex mess that is the business, we no longer have to worry about every possible state and every possible configuration of that business, because Kaufman is showing us that the only thing that's actually going to happen is that this complex system will cycle through a much reduced number of attractors. So we don't have to capture every detail and every property of every element in this system. We only care about the attractors that are possible. So this problem we're trying to solve suddenly just got much, much smaller. 2 to the power of 100,000 to 317. Not actual numbers, though. So what we have to do is build a system that works for these attractors. And the problem when a software architecture fails is most often that we build for 1 or 2 attractors that our stakeholders tell us about. And then we get surprised by all the other attractors that exist in the system because we're not able to see them. So how do we find these attractors? Well, random simulation. We just make stuff up. Which is what we've been doing anyway, but now we're going to formalize it. So an example of a stressor, something that I will make up to find an attractor is, I will say, what happens if a competitor drops their price? And then you have to figure out, well, that's the X, that's the thing that's going to stress us. What's the attractor that the business system will arrive in when that happens? And as a business, you've got to respond to the competitor's price drop. You've got to change your offering. You're maybe going to exit that market. You're maybe going to change your suppliers. And then we ask, what impact is that going to have on my software system? And the impact is that the software system doesn't survive. You have to go into your architecture and pull it apart and put it back together. And someone will say, who architected this? This is difficult. This is hard. And then you'll hide under the table and blame the stakeholders. But if you've ever reviewed a system, you know it's the easiest thing in the world to say, if you just used this pattern, if you just added this component, we wouldn't have all these troubles. And that's what we're going to do. We're going to say, well, let's add this component, and we park this architecture over here, and we call this residue number 1. This is what we would build if we wanted this system to survive in this attractor. And you come up with something else, and you do a second one, and a third one, and eventually what you end up with is your original naive architecture, and then as you explore the stressors and attractors, you end up with a whole bunch of residues. And these residues are now the unit of software architecture. Architectures are made of these things. And this isn't two-dimensional anymore, this is over time. And what happens when you integrate all of these together, all of these residues together, and this is the thing that was curious. When you integrate all of these residues together, you get a system that suddenly starts to survive things that weren't in the specification. And my research project started because I looked at this happening over and over again. I was doing it in my projects, but I had no idea why this was happening. And I thought, is this just luck? Why does this keep happening? And it turns out, and it only took 10 years to figure this out, it turns out there's a very simple mathematical leverage at play when we use this kind of method. When I have identified a residue, that residue will survive in at least one attractor, but generally, it doesn't have to be so, but generally a residue will survive in multiple attractors. Every one of those attractors has a large number of X's, a large number of events that can happen in the system that can push the system into that attractor. And that makes sense because there's way more events that can happen than there are attractors in a system. All I have to do as an architect is identify one X, and this X here, and then I will have identified this attractor, which lets me identify this residue, which survives in all these attractors, which survives all of these X's. And this gives the system the impression of being a little bit magic. And when you go, and senior architects, any senior architect who's been around for a long time and built big systems has already figured this out. Now, they might not be able to formalize it or describe what they do, but they know what they have to do to trigger this behavior. And sometimes we call it requirements, and sometimes they call it risk, and sometimes they call it DDD, sometimes they call it TDD, but they're all doing the same thing. They're getting to this mathematical leverage. The problem is that they can't really express what they've done because we're not taught to think in this way. So when you go to a senior architect, and if you'd gone to me 11 years ago and said, how do you do this? The answer is, I'm magic. And that doesn't help a junior developer who wants to become an architect. And the only way to become an architect then is to follow those senior developers until you too learn how to do this. There are a few things, though, that stop teams and stop architects from being able to do this. One of them is called the curse of dimensionality, which is what happens when you're randomly simulating an environment. You tend to simulate only those things that you believe are actual, that you believe are actually going to happen, and that introduces bias. And that's why traditional requirements and risk management can't actually work in these scenarios. And what that does is it gives you a very skewed picture of what the circle actually is. And if you put human beings together, everybody wants to be friends, everyone wants to have consensus, so we all throw darts at the same place to make ourselves feel good, and that reduces our ability to do this. The way to fight back against this is to introduce lateral thinking, to get people used to thinking a little bit outside the box, to get people used to thinking outside of their biases and outside of the biases that are introduced by stakeholders. So one of the stressors that I introduce is this idea that giant fire-breathing lizards will come up out of the North Sea and destroy Copenhagen. What's left of your business? And we don't do this with management. They don't get it. Because the first thing they'll say is, there are no giant fire-breathing lizards in the North Sea. And you'll say, how do you know? And what this does, though, if I solve the problem, if my data center is here in Copenhagen, the residue isn't particularly good. Everything's burned down. Maybe I'll have a data center in Stockholm, let's say, and then I've solved the problem with lizards, which is this X here. Now I have a system that will survive lizards, but it will also survive flooding and social unrest and war, invasion. It will survive pandemics, where Copenhagen is still here. There's no lizards, but nobody can come here, so it's kind of the same scenario. And so what we've done is we've used the stressor, which seems ridiculous, to describe an attractor that could turn up by any myriad number of ways. And we survive those things. So I'll give you a concrete example to show you how this works. So we're building a system, a cloud-based system, to manage a global network of electric car charging stations. And the way this is going to work is that a customer will come in, give us their credit card details, and we'll send them a little key ring in the post, and they drive up to the charger, and they hold up the little key ring, and it does its little blip thing, sends a message up to the cloud with an ID. The cloud system looks up the ID, says, yes, you've paid your subscription, sends a message back down to the charger, which allows it to charge. That's the naive architecture. That's where we start. And then what we do is we start stressing the system. And we start putting stress on it and discovering residues. And there's a lot of stressors here. This is a sort of politically correct sample of stressors that you show to management. There's no lizards in here. But there's an interesting trend here that you'll see very, very quickly if you start using these ideas. The first thing that's interesting is number 3, the residue that we have here. What happens when the little key ring doesn't work? What's the residue? The residue is that you have someone parked in front of a charger. They may not have enough battery to go anywhere else. They cannot get the charger. They cannot get this to work. The key ring has been put beside a magnet or chewed by a baby or something. It won't work. They are not going to move. And you're going to have a queue of other customers who want to use the electric charging station. They're getting angry. There's only one telephone number on the charger at this point, and that's the emergency number, because these things are run at about 50,000 volts, and they're very dangerous, and you have to have a telephone number. And so some poor technician gets woken up in the middle of the night. Their job is to come and save your life if you're getting electrocuted, and they're getting calls about this key fob. We have to solve this in a different way. And the way we solve it, the little green box, is something called ALPR. Automatic license plate recognition, so that when you drive onto the lot, we scan your license plate, we let you charge, regardless if we know who you are or not, just to get rid of you, so that we don't annoy our other customers. And then we'll look you up in whatever country's database it is and send you a bill and an offer to become a customer after that. It's actually a better business model. The next thing that's interesting is number 8, and that is that people are going to drive into these things. And so we have to allow for the fact that 1 or 2 of our chargers on every lot are going to be damaged all the time. And so we introduce redundancy, and we introduce security cameras to see who it is that's driving into our things all the time. And the next thing that's interesting is stressor number 12 here, where a customer will drive up, plug their car in, and go away for a very long time. And the intention was that they'll plug in for 25 minutes, it's a fast charge, and then drive off, and then the next customer can use it. But at shopping centers and at golf courses especially, people will plug in and go away for a very, very long time and hog the charger. And so we change our business model using our ALPR to read how long someone is there, and we invoice per minute on a sliding scale. Now, so far, what I've described is ordinary, normal business development. But because we've been stressing and changing our architecture, we start to see a pattern. And the pattern appears first with this thing called icing. ICE stands for internal combustion engine. It's how the electric car industry talks about fossil fuel-driven vehicles. And icing is a phenomenon that starts in the United States. And the way it works is that people, for various reasons, are irritated by electric cars. They don't like them for some reason. And so what they do is they park their ICE vehicle, their fossil fuel-driven vehicle, in front of the charging station. Now, some people do this just because it's a parking space. Some people do it because they want to irritate electric car owners. And what they do is they park their car in front of the charger, they jump out, they do a little dance, they video themselves, they put it up on TikTok. Other people see it and say, hey, that's really cool. I want that on my TikTok account too. And it spreads very, very fast. This is one of those X's, one of those things that you're not going to capture in traditional requirements engineering. You're not going to capture that kind of thing. But this system that we built will survive this unknowable stress because, firstly, we have your license plate, so we're sending you a bill regardless. Secondly, we have redundancy, so if you really want to hurt us as a business, you better bring all your friends. Thirdly, we have security cameras for the inevitable police report because this is sabotage. And fourthly, we're charging you per minute on a sliding scale. If you do this to us, we as a company will make more money, while our competitors are getting damaged by this. And this is the kind of effect we see all the time. When you build your system by constantly stressing it, the system starts to be able to cope with things that aren't in the spec. And you'll find that very similar idea in a book called Anti-Fragile by Nassim Taleb. It's not just an American problem, though. A year or so later, in Munich, someone makes a connection between the ownership of electric cars and vegetarianism. And they think, I'll show those vegetarians. And so they stuff mincemeat into the charger. And I don't care which enterprise architecture framework you're using, I don't care what requirement specification tool you're using, you are not going to have someone sticks mincemeat in the device in that document. You need a different way to cope with these modern problems. What we're actually doing is we're changing, when we start to think in this way, we're changing the definition of what architecture is. When you learn to be a programmer, your focus, your goal is to be correct all the time. Your program has to be correct. Your code has to be correct, right? Hopefully. And with an architecture in a complex environment where we don't know the future, we cannot be correct. We have to let go of that need to be correct, and that's hard for a lot of people in our industry. In Kaufman terms, if you think about a system in terms of n, the number of nodes, and k, the linkage between those nodes, you can choose to build a system with very low n and very low k. And in our industry, that's a low number of components and a low number of connections. And in our industry, we call this a monolith. You can also choose to build a system with very high n and very high k. And in our industry, we call that microservices. And obviously, both of these kinds of system have their disadvantages and advantages. The monolithic system down here with low n and low k is going to be very fragile. It's going to break very easily. When we push on it from any direction, lots of the system's going to fall over. The microservice system is going to be better than that, because when you push on the microservice system, you can only kill a little bit of it at a time. But if you've got your microservice decomposition at the wrong level of granularity, whenever you push some of those components over, it's going to have rippling effects through the system, which is going to take operations 3 weeks to figure out what actually happened. And what happens is, in biological systems, this happens as well. If a system has too low n and too low k, it dies out very quickly, because it has no ability to adapt or change, and it all dies when something happens. In a biological system, when n and k are far too high, the system collapses under the weight of managing itself. And so cancer is an expression of n and k being perhaps a little bit too high. Kaufman defines a property called criticality. And criticality is when you have the right balance of n and k in your system to survive things that you're not aware of already in the future, but not so high that you die under the weight of managing it. And he draws this line, this optimum line between n and k, and he calls this line the edge of chaos. You've probably heard management consultants use that phrase, but they don't actually know what it means. What we're doing is we start off with a simple architecture and we stress it. And when you stress it, when you stress your simple architecture, it tends to break up. You add new components, your n and k rises. And as you stress it more, n and k continues to rise until you get to the point where you see, the icing stressor, that the system pushes back. It survives something that isn't in its specification so far. When that starts to happen, it means that your system, from a complex systems perspective, has reached the point of criticality. And criticality, as we've said, it should be the goal of the software architect. Our goal is not and cannot ever be, and should not ever have been, correctness. The only thing we can deliver as architects is criticality. And so finally, I'll say a little bit about how we integrate all of these things together. So that's how you bring the random simulation in and make it better. Now we're going to look at how we make the NKP analysis more explicit. And that's through something called contagion analysis. So this is a typical architecture. And this architecture is one of those architectures where I've thought a little bit about things. I've tried to encapsulate all the things that I know are going to change. But it still suffers from this problem. X, the stressor in the disordered business environment, will turn up, and perhaps it'll knock on one of my components. The reality is that it usually knocks on more than one component, and it's usually unexpected. You can see in this diagram that C and G are fairly far apart from each other. They should be separate from each other, but suddenly this stressor pops up in the environment that I didn't know was there, and it hits both C and G. In network science, when you have a relationship between nodes like this, the stressor's connected to C, the stressor's connected to G, that implies that there's a connection between C and G. And by connection, in our industry, what we mean by that is coupling. C and G are coupled, but we didn't know they were coupled until this unknowable stressor popped up in the environment. And so what we have is an invisible link. And it turns out, when you run this kind of stressor analysis, you'll find that there's an entire spider's web of invisible links in your application. This is what makes an architecture poor. It's what makes an architecture fail. It's what makes operations costs for your system rise. This is the danger of not doing software architecture. And because we have a fairly good grasp on the functional coupling between our components, since we designed them for a specific function, a lot of these spider's web, these lines, actually reveal non-functional requirements. And this is a much more effective way of finding non-functional requirements than taking some poor business manager and saying, what are your non-functional requirements, and then watching them sweat and make things up. How do we deal with this? It's actually really simple. We run the NKP analysis by using something called an incidence matrix. And what we do is we take our list of X's, our list of stressors, we take our potential functions that we see are going to need to run in this application, and we go through the matrix, and if a particular stressor hits a particular function, we give it a 1, and if it doesn't hit it, we give it a 0. And then we total up all the rows. And this very simple matrix gives us a whole bunch of clues about where we need to refactor, where the boundaries in our application might be slightly off. And so what we do is we take the biggest numbers, because we want these numbers represent K in our network. We want to get these down. So we take the biggest ones first, and we say, why is something hitting all these things on a server failure? And that's fairly obvious that someone's decided to put all of these things on one server. So we introduce redundancy, or we push things out to Kubernetes, some technical refactoring to get that number down. Then we look for the components that perhaps get hit the most often. And we say, what's wrong with this component? And there's a number of possibilities here. Perhaps we've pushed too much into one function. We're doing too many things. We've violated SRP grossly. Or perhaps it just is the case that this particular function is absolutely vital to the operation of this system, and we have to protect it through redundancy and recoveries and retries and resilience patterns and things like that. Another thing we see is when we get zeros, for example, that's a sign that you just haven't stressed this component enough, because no component is invulnerable. All components can be broken. And if you can't find a way to break it, then it's a failure of imagination. You need to bring someone else in, someone more negative, and they'll figure out for you how this thing will break. Another thing that turns up is that we find this coupling. So anytime you have two ones in a row, you've discovered this invisible coupling, and it reveals a non-functional requirement, and it helps us catch these things. And one of the coolest things that comes out of this kind of matrix is that any two functions that have exactly the same response to stress are going to live and die together forever. And what you've discovered when you see that is a component boundary, in a way that's traceable, in a way that isn't based on opinion or conjecture or a blog post you read, but an actual bona fide traceable way of saying, here's my component boundary. That can give you some weird effects where you get some functions living beside each other that don't actually belong to each other, but you don't have to follow the rules either. And this simple matrix allows us to refactor our system to make sure that we aren't integrating those residues in a way that they restrict each other. And finally, the thing that we can do is that we can prove, using these ideas and changing our architectural methods in this way, gives us the possibility of proving that we've done something useful, which if you're an architect, might be the first time. We have our naive architecture, and what we do is we produce a list of stressors, a list of things that are going to hurt it, and we use that list of stressors not to specify our solution, but to train our solution to be able to survive. And what the result of that is our residual architecture, our new architecture. And what we then do is we take a second list of stressors, which we kept in a drawer somewhere, or we go and get someone else, that negative colleague, we'll call him Barry, to stress the system for you. And you take this red list of stressors, which neither of these two architectures have ever seen before, and you run them over the naive architecture, and you say, did it survive this stress? And if it survives, it gets a 1, and if it doesn't survive, it gets a 0. And you do the same thing with the residual architecture. If it survives the stressor, it gets a 1. If it doesn't survive, it gets a 0. You add all these 1s up, and you call it x for the naive architecture and y for the residual architecture. And then you calculate this little thing called the residual index, y minus x divided by the number of stressors in your red list, which gives you a value between -1 and 1. And if the value is greater than 0, you have done good work. You have built a system that is more likely to survive off-spec requirements than the original system you started out with. You've actually made an improvement. And when I run workshops like I ran this week on these things, in the workshop we actually run these numbers and we run it over a bunch of groups, and it's pretty easy if you've got more than 15 people in the group to reach a statistically significant result, even in the workshop. And so it's pretty easy to prove that this has an empirical backing. This actually works. And that's a bit different than how we normally do architecture. Normally, I can just get up here on a stage at a conference and make stuff up, and nobody will ever check it. But this is empirically verifiable, which is a step forward for us. Now, there is some confusion, and this question is probably popping up in some of your heads, that some of this feels kind of familiar. Traditional methods, and people tend to get what I'm talking about confused with traditional methods, and that's because we tend to look at a new idea through the lens of old ideas. We try to understand the new thing by saying, is it like these old things? People tend to confuse what I'm talking about here with risk management, with edge cases, with scenario analysis, or even with requirements engineering. These traditional methods are all measurements. They're all looking for R. They need to be accurate, and they need to be filtered, because we're trying to create a specification, and we filter by probability, we filter by impact, we filter by what the hippo says, what the highest paid person in the room thinks. And these are point predictions to produce a specification against which we will build software. That's what we've been doing traditionally. What we're doing here is random simulation. We only use stressors. We produce many more points. It's much wilder. The probability of everything is exactly the same. There's no probability in this at all. And we converge on a solution rather than producing a spec. And the focus is not about building the spec, it's about surviving off-spec events. That's what we're doing here. And this seems to be a little bit hard to grasp. But if you find it hard to grasp, just do some reading on random simulation, on things like Monte Carlo simulations, and the difference between that and point prediction. Scientifically and philosophically, it's two very, very different approaches. But it seems to be a little bit abstract. And if you're used to working in that ordered software world, it might take a while for these ideas to hit home. So that's everything for me. Like I said, that was intense, right? There's a lot of stuff, a lot of new terms, a lot of ideas. We're kind of pulling the rug out from underneath you. A lot of traditional ideas are getting bashed over the head here. Don't expect to come away from this remembering everything or understanding everything. A guy came up to me at a conference a few years ago and said, this is the 4th time I've seen this talk, and now it makes sense. So don't worry if you have to go back over these things. This is a 45-minute introduction to 10 years of work. It takes a bit longer for these ideas to sit. This is the book. I produced a bunch of academic articles. I got the feedback from developers that we can't read this. What is it? It's too heavy. So I've written a little book to help you get started. The QR code will take you there. It's on LeanPub. Thank you for coming. Thank you for listening. And enjoy the rest of the conference. Thank you.